which focuses on the stereoisomers. And here are the learning outcomes. So you are going to learn how to recognize and assign the configurations of two new stereoisomers we are going to teach, the enantiomers and the diastereomers. And we are going to draw molecules as perspective drawings and facial projections. So facial projections are also new here. We just learned Newman projection in the last chapter. And this time we'll learn a new projections called facial projections. Okay, we are also going to learn to distinguish between the properties of between enantiomers and diastereomers and the differential properties of these stereoisomers. Okay, so the first question I'm going to ask for this chapter is that a very common question. So how do you know if two objects are the same? It's kind of silly, right? But if you have two objects before you, how do you know they are the same? So the test people usually do is called a superimposability test. So what does that mean? So if two objects are completely superimposable, then the two are the same, which means they are exact copies of each other. So if two objects are not superimposable, then they are unique and different from each other. Okay, so you just put two objects together and see each part of the objects, are they the same with each other? Okay, so for example, if I put forward like all these Coke cans, so you know that they are the same, right? Because they are of the same shape, the color, and all these fonts, they are the same. So we say it passed. It passes the superimposability test, so they are the same. All these bottles or cans of Cokes are the same. But if I have different flavors of Cokes, then they cannot pass the superimposability test because you can see, although the shape are the same, but different parts have different colors and they are different flavors, it represents different colors here. So you know that they are unique and different from each other, and because they are not superimposable. Okay, so then the concepts I'm going to introduce to you is achiral and chiral, the concept of chirality. So a very easy way to distinguish between them is that if an object has a non-superimposable, we just learned the concept of superimposability. So if an object has a non-superimposable mirror image, it is chiral. Okay, so here is your left hand, and its mirror image apparently is your right hand. Okay, and your left hand and the right hand are actually not superimposable. If you put them together, you can see, oh, I cannot superimpose them. So they're different. Okay, then we say your hand is chiral. Okay, that's the same with your ears, and also different cars in different countries. For example, on the left, that's cars in the US. On the right, that's a typical car like in Britain or Hong Kong, right? You know, they are chiral because they are mirror image, but their mirror images are not non-superimposable. All right, and but if an object has a superimposable mirror image, it is achiral. Okay, so for example, this chair. So the mirror image of this chair is the same as the chair, the original chair. Okay, so then we say it is achiral. So is the forks and so is the cups. All right. And a deeper question about chirality is that, oh, okay, we can use this test, the mirror test, to see whether it's achiral or chiral. But why are some objects chiral and others are not? So that's a question that we're going to talk about in this lecture. And what qualities make chiral objects chiral? Okay, and I'm going to introduce you another test, which also a test for whether to test whether an object is chiral or not. So the simple question is, does it have an internal plane of symmetry? All right. So let's see the Erlenmeyer. Okay, and you can find an internal plane of symmetry. Okay, you cut it here, then you can see the left part and the right part. They are the same. Okay, and for your hand, you cannot find an internal plane of symmetry. All right. If you cut in half, the left part and the right part are not the same. But for this lobster, it is achiral because it has an internal plane of symmetry just in the middle of the lobster. All right, so So I found out a mathematical way to prove that why the internal plane of symmetry makes an object achiral. All right. So if an object, let's say, composed of A and A prime, it has an internal plane of symmetry. All right. And then if you have a mirror image of this combined object, you have small a prime and small a. So the rational now is like this. So big A prime and the big A are mirror image, right? Because it has an internal plane of symmetry. So big A prime and the small a prime, they are also mirror image because they are, reflected through the mirror we just listed here. Okay, so because big A and small a prime are both mirror images of big A prime, so we can say that big A and small a prime are the same. All right, so the left part of this object is equal to the left part of this mirror image. So you can use the same logic to say that the right part of this object is as the same as the right part of its mirror image, the object in the mirror. Okay, then we can say big A plus big A prime and small a plus small a prime are the same. So the mirror image of them are the same. That means if an object has an internal plane of symmetry, we can conduct the conclusion that it has the mirror image of this object is the same as itself. Thus, it is achiral. Okay, so this is a concept. So you don't need to memorize all these logic and proving process, but just to know that if an object has an internal plane of symmetry, it is achiral. So if you move the concept of chirality into the organic chemistry, you know that for the 2D objects, it have an inherent symmetry plane, which is the plane itself, right? For a 2D object, the plane itself is an internal plane of symmetry. But organic molecules do exist as three-dimensional objects, though thus can be chiral. Okay, if you look at these two examples we have learned in the last chapters, one is testosterone and the other is glucose. They are both chiral molecules because they are 3D structures and you cannot find an internal plane of symmetry, just as we studied. Okay, and the study of synthesis of these chiral organic molecules is actually one major direction of organic chemistry. So for example, in this department, my group and Professor Pauline Chu's group, so we are both study the properties and the synthesis of chiral organic molecules. So basically it's a very big branch of organic chemistry that there are a lot of to explore. Okay, so we just say that organic molecules can be chiral, but some of them are achiral. So it can be chiral, but it doesn't mean that every one of the organic molecules are chiral. Okay, so let's see some example that are organic molecules in 3D shape, but are achiral. Okay, so that's the structure of propionic acid, and you can see it has 1, 2, 2 sp3 hybridized carbon, which means it has a 3D structure, right? But you can find an internal plane of symmetry right in the middle of the molecules. Okay, the left and the right are equal, or the above and the below are equal. Okay, so it is achiral, although it is 3D. The same is applies to the cyclohexane. Okay, it is a 3D structure with a chair conformation we just learned, but in the middle there is a plane of symmetry, so it is achiral. So if you have the dibromochloromethane, and you also can find an internal plane of symmetry, which is in the middle between these two big bromo atoms. So okay, and the green chloride and the hydrogen are exactly on the plane of symmetry, and the above bromide and below bromide are mirror image to each other. So it's an internal plane of symmetry. Thus, this molecule is a chiral molecule. But some organic molecules, I would say many of them, do not have internal planes of symmetry, thus are chiral. Okay, so the left one, what I show you that it is like the propionic acid, but it has a substitution on the 2 position, so which we call the lactic acid, and it's a plus lactic acid. On the right, it's minus lactic acid. Okay, and you can see they are mirror image, right? The OH point towards you, the OH points towards you, H in the back, H in the back, right? But if you put these mirror images together and compare them, do the superimposable test, so superimposability test. So you can see we put the CH3CCOH right in this shape, and you can see if we put them close together, you can see the OH is now pointing to you, but for the minus, the OH is pointing away from you. So these are not the same molecule, but these are mirror image, so they are chiral. All right. Okay, so we know that lactic acid is chiral. So because there are two different lactic acids that are mirror images of each other, but they are not superimposable. And we call these kind of molecules which has mirror image that is non-superimposable with the original one, we call them enantiomers. Okay. So what gives lactic acid chirality? Why after we put an OH on the second carbon, now it is chiral, but the propionic acid without this OH is achiral. So because a fundamental reason for this chirality is because it has a stereocenter, which is the carbon 2. Okay, so the stereocenter is defined as a carbon or atom with 4 different substituents. So in the lactic acid, you can see the carbon now, in the propionic, so which is CH2, it has 2H, which are the same. But in here, you have 4 different substituents: 1 carboxylic acid, 1 OH, 1 H, and 1 methyl. And this make it a chiral center and make a lactic acid a chiral. So you will probably see a lot of similar items like stereocenters, for example, stereogenic centers, chiral carbon, but they are the same. Okay, they are similar or the same. And the word we are going to use most frequently in this course is stereocenters. Okay, you need to keep this concept of stereocenters in mind very clearly. All right, so some of you may ask, so stereocenter, it is because it has 4 different substituents. So what happens if it has only 1 type of substituents, 2 types, or 3 types of substituents? So I listed several examples. So for this one, chloromethane, it has 2 types of substituents, right? So 1 H, 1 chloride, but H has 3 of them. So you can actually find the internal planes of symmetry here. So this is the what the actual molecule looks like. And 3 hydrogens are very symmetric to each other. So you can find 1, 2, and 3 internal planes of symmetry. So it is achiral. So what if it has 2 substituents, but each of them have two of them? Okay, so let's say dibromomethane, 2H, 2 bromide. So you can actually find the 2 planes of symmetry. For example, this one and this one. Thus, it is achiral. So how about 3 types of substituents? 2 bromo, 1 chloride, and 1 hydrogens. All right, you can still find the internal plane of symmetry, just right across the plane of the bromine. So now the bromide is on the 2 sides, but they are mirror image, and these 3 atoms are on the plane of symmetry. So it is also achiral. So you see, as long as the atom doesn't have 4 different substituents, so you can always find internal plane of symmetry. Thus, these molecules are always achiral. Only when you have 4 different substituents that makes the molecule chiral. Okay, let's do a small practice here. So let's find out all the stereocenters of the molecule. Remember, the definition is that a carbon with 4 different substituents. All right, so let's see, how about this one? CH3, no, right? Because you have a 3H group. Or how about this one? Well, it looks like a stereocenter, but it has OH, a big long chain substituents, but again, 2 methyl. So if you have 2 methyl, it's not a chiral, it's not a stereocenter because now there is only 3 different types of substituents. How about this one? This one is a methyl, a hydrogen, this part, and this part. 4 different, right? Yeah, stereocenter. So let's mark it here. This is a stereocenter. All right. So how about this one? This one has 2 hydrogens. No, right? And this one, chloride, hydrogen, left chain, right chain. It is. So CH2, no. This only have 3 substituents. No. This has a H, a big chain, but 2 methyl. No. So there are 2 stereocenter into this molecule, and it is definitely achiral in here. All right. So let's change back to laser pointer. Okay. So all I have shown you are linear molecules. So how about cyclic molecules? Because it has a ring, so it makes it a little bit confusing, right? So that's the way we do it. So in cyclic molecules, you just compare substituents by following each direction in the ring. So this carbon, it has a hydrogen, CH3, different, right? On the left, it has CH3, CH2. On the right, CH2, CH2, CH2. This they share together. So you can find an internal plane of symmetry. Thus, this is achiral. Methylcyclohexane is not chiral. Okay, how about this one? 2-methylcyclohexane. Okay, so methyl hydrogen on the left, CH2. This one, oh, it's a ketone. So these two are different, and all four of them are different substituents. Thus, it is chiral. Okay. So here is a more complicated example of cyclic compounds. Again, testosterone, and how many stereocenters in there. So after class, you should be able to look this molecule slowly and see how many are them. So let me just show you a little bit. So this is CH2. No, no. This is 3 substituents. No, 3 substituents. No. For example, this one. 1, 2, 3, 4. Different, right? CH2. No, no. For different, yes. This is also for different, but no, no. For different. CH2, no, CH2. But this one, 1H, 1OH, left, right are different. Okay, this is also a stereocenter. So you may spend some time after class to really figure out all these stereocenters. All right. So how about the properties of enantiomer? So let's talk about physical properties first. Okay, enantiomers are stereoisomers. They are similar, but they are different. Okay, so enantiomers have the same physical properties, except optical activities. For these same properties, you can see the plus tartaric acid, minus tartaric acid, they are enantiomers. Okay, and they have the same melting point, same density, same solubility, but optical activity, they are exactly opposite to each other. So enantiomers have different optical activity. So you may wonder, what is optical activity? So the optical activity is the ability of the molecule to rotate plane polarized light. So we have a normal light, right? And the normal light is usually all directional. The light is radiated in every direction. But if we put a polarizer before the light, then if the light goes through the polarizer, only one direction light remains, okay, the up and down, up and down. And if this light goes through a sample tube containing a chiral compound, the chiral compound can interact with the light, okay, through energy absorption, energy loss, something like that, very physical stuff. And then the light can rotate, okay. You have your eyes here, you can see the light turned from the upright position to alpha degree, okay, some angle. Then all these compounds that can rotate polarized light are called optically active compounds. So, and the properties of optical activity is expressed as the specific rotation, which we call the alpha D. So the alpha D is a characteristic property. So it is a property just like the melting point, boiling point. They don't change because it's the property of a molecule. Okay, and so specific rotation alpha D is defined by the angle of deflection, the angle of that it rotates, observed for 1 gram per ml in solution in cell with this type of this length and this nanometer light, okay, with the sodium light. So it's defined by the formula is here. So to calculate the alpha D of a molecule, you have the observed rotation, and it's divided by the path length. For example, the length of the cell, and you put your molecule here, and also divided by the concentration of your sample, the concentration of the sample you put in the cell, and so in reality, what the observed rotation is observed from the polarimetry, okay. And then with the known, you already know the length of the cell, and you already know the concentration of the sample you prepared, right? Then you can know the specific rotation of a compound, all right? And then again, if I ask you for a molecule, all right, it has a property of the specific rotation, right? So if I increase the polygrammetry cell's path length, like I use a longer one, so what changes with the observed rotation? It will change to a bigger value, right? Because the observed rotation equals the fixed number times the length and the concentration of your sample put in your cell, right? So if the length increases or the concentration increases, the observed rotation that is read from the instrument will increase. Okay, so keep that in mind. So specific rotation usually have a plus or minus sign, but no degrees. So we say it has a specific rotation of 12. We don't say it has a specific rotation of 12 degree, okay? And some definitions here: compounds that rotate the plane polarized light to the right. It's called dextrorotatory. It's plus, and the opposite, if it rotate the plane polarized light to the left, it's called levorotatory, which is minus. So you can see all these drugs and organic natural molecules like penicillin, sucrose, camphor, cholesterols, they'll have different specific rotations. Some of them are positive, the other are the levorotatory, which is minus. Okay. So this is also a very good opportunity for you to practice on all of these concepts we have learned from the past in the last week. Okay, so you may be able to search for all these structures of these names that you can find them. Many of them are very, very complex structures, and you can figure out, okay, how many primary, secondary, tertiary, and quaternary carbons are in each of them, and how many stereocenters. All these carbons with 4 different substituents, and what type of string. So we just learned the definition of torsional string, angle string, and steric strings. So do they have all of them or any of them? All right. So how did people originally find the specific rotation? Okay, or the chirality phenomenon. So one of the early example is by Louis Pasteur. So what he found is that there is one acid called the parataric acid. People usually find this on the cork of the wines, okay? And it has no optical activity at all. But what Pasteur does is that he forms salt of these compounds and recrystallizes them. And he found that non-superimposable mirror image crystals. Okay, that's really interesting, right? He actually isolated 2 crystals that is mirror image to each other. And they are non-superimposable. So that probably means the compound is actually composed of 2 enantiomers, right? And 2 enantiomers can grow into a different non-superimposable mirror image crystals, okay? So he separated them, and he found that the compound, yes, is composed of 2 different compounds. One is the plus tartaric acid, the other is minus tartaric acid. So the plus one has 12 specific rotation. The other one has the exact opposite specific rotation, meaning that they are enantiomers. Okay, so after the physical properties, let's talk about some chemical properties of enantiomers. So the phenomenon you are going to learn here is called a chiral-achiral interaction and chiral-chiral interaction. So enantiomers react with achiral compounds in exactly the same way, but enantiomer may differ in their reaction with other chiral compounds. Okay, so some real life examples. So many hotels have these achiral slippers. So you have your chiral feet, right? But you wear these achiral slippers, they both feel comfortable. Okay, so that's what we call a chiral-achiral interaction. Okay, but that's a different case for your running sneakers, right? Or your shoes. So your shoes have left feet and right feet. Okay, so you have chiral feet, and your shoes are also chiral. So now we found out that if you wear your left sneaker into your right feet, it causes miscomfort, which means that it's mismatching. Okay, there is some energy difference between your between the left to left and the left to right sneakers. Okay, so on a molecular level, so we have this example, which show if we have a 50-50 mixture of ammonium tartrate, both containing both plus and minus, if we try to hydrolyze it, so if we use achiral acid, let's say hydrochloric acid, then we have both acid product. Okay, both the plus and the minus react with achiral acid. Okay, that means the achiral compounds react with enantiomers in exactly the same way. But if we do the hydrolysis in yeast, so yeast is a biological machinery containing a lot of chiral stuff like enzyme, proteins. Okay, now you have a chiral-chiral interaction, and the result of the chiral-chiral interaction is that the minus ammonium tartrate doesn't really want to react with the chiral yeast. Okay, only the plus ammonium tartrate react to give the tartaric acid. Okay, so because the reactions between plus and yeast and the minus yeast have different energy level. It's like your left feet to your left sneaker and your right feet to your left sneakers. They are different in energy. Okay, left to left is comfortable, lower in energy, but right to left is discomfort. Okay, it means higher in energy. The same with the molecular reaction. Okay, then we need to learn how to draw enantiomers. So if you recall how we draw the sp3 tetrahydrocarbon, so we have a bold bond, we have a dashed bond. So the bold bond means the bond is pointing to you, right? The dashed bond means it's pointing away from you. Okay, so these are called perspective drawings. Okay, and up to now, perspective drawings of stereocenters at a tetrahydrocarbon remains the most frequently used and accurate way. Okay, so if you draw a complex molecule with the perspective drawing here, you know that the methyl is pointing to you, and you know the hydrogen, the oxygen is also pointing to you. Okay, but another representation called Fischer projections are really good at other things, which most of them are like molecules with consecutive stereocenters. All right, it is really good for Fischer projection to be used. So what does Fischer projections means? Okay, so you have a carbon stereocenter, right, with 4 different substituents A, B, C, and D. If you look through this direction, what you see is here, right? So the C and D are pointing to you. A and B and pointing back. So if you draw a bold and a dashed angle, a dashed bond, you can draw like this. So if we simplify them, we eliminate all the bold bond and dashed bond, just plain bonds, okay? Then this is called a Fischer projection. So if you see a Fischer projection like this, you know that C and D, which are horizontal groups, are pointing towards you, and A and B are pointing away from you. So actually, there could be multiple Fischer projections for a single molecule. For example, these 4 molecules are the same. I just present them in a different way. Okay, A and B. If you flip them, now the D becomes in the front, right? So if you look through this direction, you can actually draw 4 different Fischer projections. C and D point to you, C and D point to you, different direction. DB pointing to you, BD pointing to you. Okay, so that creates a lot of confusion, right? So to make Fischer projection really clear and accurate, so we have some conventions to follow. So the conventions are that carbon chains are placed on the vertical. So what that means? So if you look through this direction, these 2 alkyl groups pointing to you, right? But do not draw like this, because if you draw like this, you put the alkyl group on the horizontal, not the vertical. So a preferred way, a correct way to draw a Fischer projection of this molecule is that you put the alkyl group on the vertical. Now you have two Fischer projections that put the alkyl groups on the vertical. One is the longer chain in the upper, and the one is the SO on the upper, right? Both of them are correct. Okay. But an interesting phenomenon is that this is exactly the same drawings like this after it turns 180 degrees, right? We put the chloride here, hydrogen here, this big one below, SO above. Okay, so that is also one of the important concepts of facial projection, is that if you rotate 180 degrees of one facial projection, the facial projection resulting from the rotation represents a molecule that is the same as the original one. Okay, so for this one, the big chain is here, and so you look at through this direction, right, in the above, then in the below, and then chloride on the left and on the right. If you rotate 100 degrees, that's exactly another way to look at through this direction. Is you put this SO on the top, right, this one on the bottom, and now the chloride is on the right, and the hydrogen is on the left. Okay, so you rotate 100 degrees, 80 degrees, and they represent the same molecule, but you cannot rotate 90 degrees of a facial projection because they change the molecule it represents. Okay, so if you change this one 90 degrees, you put the SO here, you put the SO here, longer chain here, the molecule now represents this. Okay, so what's the relationship between this and this? So it's an enantiomer, right? It's enantiomers. So you rotate 90 degrees, the facial projection actually represents a molecule that is enantiomer from the original molecule. Okay, so if you see two molecules that is 90 degrees from each other in facial projections, they are not the same molecule. Just keep that in mind. And as I said, facial projections are really great for representing molecules with multiple and consecutive stereocenters. For example, all these types of sugars, like the 3-carbon sugar, 4-carbon, 5-carbon, 6-carbon sugars. Okay, and you can see stereocenter 2, 3, 4. Okay, and in these cases, facial projection usually put view the molecules in an eclipse conformation. So OH pointing to you, this OH also pointing to you, right? And that makes them on the eclipsing, because this OH and this H, this OH and the H in the back are eclipsing. Okay, so the facial projection really represents the molecule not in a real conformation, but as a convenient way to draw a molecule. Okay, so the real conformation probably have these carbons like a gauche or staggered to each other, but the facial projection just to draw them as a convenient way or in eclipsing forms. So after we learn how to draw the molecules, we also need to learn how to name the molecules. So enantiomers are different molecules with different properties, so they should, in principle, have different names, right? And we know that we can name enantiomers plus and minus because we tested them in polarimetry and give different values, but that's really inconvenient, right? So if you want to name a molecule using the plus and minus, you have to test every molecule you name in the polarimetry. So that's virtually impossible. So we want a naming system that is based on the structures. So that means that if we know the structure of the molecule, we can have a name. So not that we know the properties of a molecule, then we have a name, okay? Because you have to test the property. So we want a system that's not related to the physical property of the enantiomer, but to the structure of the enantiomer. So how to name enantiomers? Okay, so you know that the stereocenter is substituted with 4 different substitutions, right? And we also call the relative position of these substituents configuration. So configuration is defined by the relative position of all substituents. So there are 2 of them because there are a pair of enantiomers. So we need a method to specify the configuration of the stereocenters. Okay, thus one specification refers to only one configuration, and vice versa. One configuration has a unique name, a unique assignment. So what we are going to teach here is that called Carr-Engel-Prelog convention, CIP convention, or CIP rules. So the step 1 of assigning the stereocenter here is to assign the properties to the 4 groups that are around the stereocenters. Okay, so now you have iodide, bromide, chloride. So iodide is biggest because the atomic number is 53. Hydrogen is the lowest. It's 1. So you can name, or you can like put the priorities to these 4 substituents. So A, the iodide biggest, B next, C next, D is the lowest. Okay, and then the step 2 of the CIP convention is that you orient the molecules. So the lowest, which is hydrogen, is in the back. So it's numbered D. So it's number D. So you put the D in the back, then you look through this direction, okay? So what you see is that 3 groups like chloride, bromide, iodide pointing to you, right? So this is a real model. So the 3 colors pointing to you, okay? And they have priorities on them, A, B, and C, right? So the third step is to name the stereocenter, okay? So if so now you need to use both of your hands, okay? So if you put your left hand out and you point your thumb to the hydrogen, to the D, okay? And you rotate your left hand, okay? So if the 3 groups pointing to you goes through, it matches your rotation of your left hand from A, B, and C, counterclockwise, okay, then it is S. We call it S, which means sinister in Latin is left, okay, because it matches your left hand. So if it doesn't, then use your right hand, it should match. So if your right thumb pointing to D and rotate your right hand, A, B, and C, correct direction, then we call it an R. So S and R are enantiomers. All right, and depends on which hand fit the direction of which hand fit your molecule orientation. And another way, so you can also name your substituents 1, 2, 3, and 4. Okay, then the 4 is the lowest priority, and you put it in the back. Put your eyes in the front, and you have a 1, 2, 3 pointing to you. Okay, if 1, 2, 3 is the right turn of the steering wheel clockwise, it's R. Then if 1, 2, 3 is left turn of the steering wheel, then it is S. Okay, and so that's the steps to assign stereocenters. Okay, so in these examples, we can see iodide, bromide, chloride are the counterclockwise, which fix the left hand. So it's S stereocenters. So the complete IUPAC name of this molecule is S, bromochloroiodomethane, and its enantiomer, of course, it's the fitting to the right hand. So it's called R bromochloroiodomethane. Right. So then next lecture we are going to learn more about the Carl-Ingel-Prelog conventions, most complicated situations, and we are going to do some exercises about this assignment. All right. So see you next time.